Hey everyone, this is Tyler Berry back for another whiteboard session. This time we're going to talk about air and water. Now, air that is contained in water is mainly described by two different laws, Henry's law and Stokes' law. And the primary two reasons for air getting entrained in water is temperature and pressure. Now, within a closed hydronic system, a lot of velocity has something to do with that as well. But the combination of those two laws allows us to get a better understanding of how much air can get stuck in water and how do we release it. So in a hydronic system, having air in the water can cause pump cavitation amongst a number of other things, and especially in boiler systems, if air gets into our boilers and that becomes our slow spot of the system, we can start having flame to metal contact and break heat exchangers. Now, there's a number of different ways to get air out of the system. One being a traditional roll air trawl air separator, and what we're doing is we're actually slowing the velocity down and using centrifugal force to release air out of solution, and that's what happens in a roll air separator. Now, the difference between an air separator and a coalescing separator is simply the fact that we have coalescing material that actually agitates the solution to not only break apart that air, but also sediment as it falls to the bottom, and then you can blow it down. The biggest thing I want you to take away is that all we're really doing outside of the material inside is slowing the velocity down below a half beat per second, and that's what allows us to get the air out. You can think of it this way. When you pour yourself a glass of water, and you set it down, sometimes you see those little air bubbles from your tap water rise out of solution. This is the combination of Henry's and Stokes' law. All we're doing is allowing the pressure to alleviate from the system. We use centrifugal force, and we get the air out of solution. Another thing to keep in mind is sometimes we have to break apart our systems, like a boiler system with a primary, secondary header. So we can use the same thing on a buffer tank. We can use that as our air separation because we're actually just slowing the system down. So if you needed a 500-gallon buffer tank in your boiler system and you're doing a primary, secondary system, well, you can provide flanges on this side, connections on this side, and you break apart this loop. And by doing this, you've decoupled your primary and secondary header, you've got your air elimination, and you allowed each flow to do its own thing. Another thing is if you're stuck in a tricky spot and you still need a primary secondary decoupler, you still need to get air removal from the system, you can do something like a Hamilton Engineering system separator, and you can actually put it in a corner, taking up essentially the same footprint, albeit taller, than your standard air separator or coalescing separator, but the intent is still the same. We want to slow down our system. We want to get air out of our system. And in this case, we can get air and dirt, but the methodology is still the same. So, once again, I hope you learned a little something about getting air out of the system, why we get it out of the system, and how it stays entrained in there. If you have any questions about design methodology or how we accomplish this, just give me a shout. Love to hear from you. Thanks again. Bye.